Hi folks, welcome back for the second half of the lesson on algebraic approaches to limits. This is going to be a fairly quick section. We're going to look at squeeze theorem or the sandwich theorem. We're going to look at an alternate way of dealing with one of the functions that we already dealt with, or one of the limits we already dealt with. And also I'll let you know where you can find a proof for sine x over x for that limit. So sometimes there are limits that are difficult to find. They're tough to track down. So if I had some function like f here, and let's just suppose that it was hard to find its limit at x equals c, or around x is c. And I had two easier functions that I could play with. Let's call one of them g of x. Let's call the other one just some random function h of x. And let's just imagine that they were, for some reason, easier to deal with. Okay. So if f is sandwiched between g of x and h of x, that's why the squeeze theorem is sometimes called the sandwich theorem, in the neighborhood of x equals c, then the limit of g of x, which is below it, must be less than or equal to the limit of f of x, the actual one we want, which is less than or equal to the one that's on top. Now, if they're all equal to each other, then I guess secretly they all have the same value. And that seems very, very abstract, but it's actually needed for the proof of limits x goes to 0 of sine x over x. We use it often for trig functions where it's tough to sub in. So here's an example. Let's use the sandwich theorem or the squeeze theorem to find this limit as x goes to 0 of x squared times sine of 1 over x. You might say, oh, we'll just sub in 0. That's no problem. You get 0 times the sine of 1 over 0. Well, 0 times anything is just going to be 0, right? So it should be done. But 0 times undefined is dicier than that. Sine of 1 over 0, we have no idea what it is. So all those rules about as long as it's 0 times something, they fall apart if we have an undefined involved. Here's what we're going to do. We're going to say, here's what I know about sine of anything. So I'm just going to start by thinking about sine of 1 over x. Okay. Sine goes to a maximum of 1 and a minimum of negative 1. Sine values cannot go higher or lower than 1 or negative 1. That's just true. Right? Now, build the thing that we want, build x squared sine 1 over x by multiplying each part of that inequality, by x squared. Okay. Now, it's conceivable in some of these cases that the direction will change of the inequalities if you multiply by a negative. That's not really happening here. But it doesn't matter because it's sandwiched in the middle of them. So we're looking for a case where they're all going to be the same. Okay, so I'm going to times everything by x squared. So I'll get negative x squared is less than or equal to x squared by sine 1 over x, which is a tricky limit to find. Okay, I times this, and this, and this, all by x squared. And here's the thing. This limit, as x goes to 0, is easy. It's going to be negative 0 squared, or 0. Okay, I shouldn't put a circle around that because that's not my final answer. That's not the thing I'm really looking for. This one, I can also evaluate its limit. Okay, as x goes to 0, well, x squared is just going to be 0 squared. I can sub in. That's simple. But if the overall limit that was hard to find was sandwiched between 0 and 0, well then it also must have a limit of 0. Even though I still can't really sub in here, I can't do a whole lot. Since I know something above it is going to be 0, something below it's going to be 0, its limit also must be 0. So that's going to work in a nice proof on the Khan Academy, and I'll link this in the video description below, that sine x over x is going to be 1 as x goes to 0. There are some practice questions in the 4th edition of Finney right here. We can take a look at what the graph of all this means. It's a very neat looking graph. You can see when you just have the graph that it is going to be going towards 0. But if I take a look at those ones that we sandwiched it between, there's x squared, and here's negative x squared. You can see that that graph that we care about really is sandwiched in between them. And since we can find out the limit on the green one and the purple one, we automatically know the limit of the one we care about, the blue one. The last thing I want to do here is revisit one of the limits that we did in the last video, just because there's an alternate approach, and there are often many approaches for much of mathematics that some of you may be interested in. So it's this one over here where we did conjugates for it. You can also use factorization here. We all know that x squared minus 4, it's going to factor like this. But secretly, I mean, every number is something squared. So what if I had x squared minus 3? Well, you could factor it as x plus root 3, x minus root 3. Or you could even say for x minus 4, well, that could be, I mean, the first one might be root x plus 2 and root x minus 2. Now, that's not quite perfect because that factored form only works for positive numbers. But in this case, we have a limit involving positive numbers, so it'll be okay. This is still a difference of squares. It's like this one is root x all squared, and this one is 2 all squared. So if you wanted to, you could approach this question a little bit differently. You could strangely factor the top, or creatively factor the top as root x plus 2, root x minus 2. And on the bottom, you've got root x minus 2. And you can get rid of your problem. We've already tried subbing in. It didn't work. And you can see that you're going to get the same result. Root x plus 2. Now we can sub in root 4 plus 2. Oh my gosh, that gives us 4. With less work. I think that that is more opaque. I think you're better off just using the conjugate stuff because we use conjugates all the time. But if you want to use this other approach, feel free. All right, folks, that's it for today. I hope that you found this helpful. Good luck with the material, and take care.